both of them in the past, polynomials and rationals. And I've got to be quite honest with you. Some of this is going to be review, but there's going to be some things that show up graphically today that are going to help us a lot with what we need to accomplish. So to get started with polynomial and rational functions, I need a volunteer to read that essential question for me.
What are the characteristics of polynomial and rational functions, and how do you use those models in your life cycle?
Okay, so we're going to be looking at some models for polynomial and rational functions and apply them. And we want to look at some end behaviors of polynomial or rational functions. I'm going to give you some shortcuts to that. But end behavior simply means, where's my graph going? As x gets very large to the right, is my graph going positive infinity, negative infinity, or is it stalling out somewhere? So we'll talk about that. We want to understand the basic shapes of graphs of polynomial and rational functions. And then we're going to write functions for given graphs. And then the last thing we need to do is understand rational functions, and we've kind of talked about this a little bit before. Some asymptotes, both horizontally and vertically. Okay?
Wait, how did you say that?
Asymptotes.
Asymptotes?
Asymptotes.
Asymptotes?
Asymptotes.
Oh, okay.
It's like Ashley Simpson totes her stuff around.
Are you saying as or ass?
Asymptotes.
Ass?
Yes, donkey-ish.
Okay.
Okay? I once knew a guy named Jack Asymptotes. Pretty cool guy. Okay?
Even if I'm having a bad day, this class always makes me smile.
Well, good. I'm glad. Guys, I kind of screwed up on the vocab for this first term, so you might want to just put the L up here. It's not polynomia, it's polynomial. Polynomial sounds kind of cool, though. Polynomia. Sounds like a bunch of killer flowers. It's like pneumonia. Like a Venus flytrap. Polynomia function. Polynomial flower. Okay. All right, hey, polynomial functions. You've seen this form right here. It says a function takes on the form a sub n, x to the n, plus a sub n minus 1 to the x minus 1, and so on, all the way down to a sub 0, where a sub 0 would be a constant. A sub n cannot be 0. The exponents are all whole numbers, and the coefficients are real numbers. Ha! That's a big, big definition for polynomial functions. The thing you need to understand, this is an example of a polynomial function. Okay? This is an example of a polynomial function because your exponents are whole numbers and the coefficients are all real numbers. You've seen polynomial functions before and you've dealt with this. Okay? So don't lose too much of what's up here notation-wise in terms of a definition. But this would be an example of a polynomial function. Okay? So a rational function is a function that has the form f of x equals p of x over q of x, where p of x and q of x are both what, kids? And q of x cannot equal what? Okay, so in this case, understand that a rational function is a polynomial function over another polynomial function. Okay? And the reason the bottom can't be 0 is what in a rational function?
The universe ends.
The universe ends. You don't want denominators to be 0, right? Okay? Alright? Although I still think 0 divided by 0 could be 1 if you consider 0 degrees Celsius over 0 degrees Celsius as 32 Fahrenheit over 32 Fahrenheit. 1. I'm okay. Hey, who wants to read vertical asymptote for me? You want to read the vertical asymptote definition for me?
No. Vertical asymptotes are vertical lines which correspond to zeros of the denominator of a rational function.
Okay, so vertical asymptotes come about when there are zeros in the what? Denominator. So take a look at this function that's graphed here. It doesn't show up well on the board, but you guys can see it in your notes. Guys, this line right here, x equal negative 3. Why is this a vertical asymptote? This vertical dotted line at x equal negative 3. Why is this a vertical asymptote? Well, what would you plug in right there to make that first set of parentheses in the denominator 0?
Negative 3.
Negative 3. Okay.
And then positive 1.
Positive 1 would be the other one because it makes the denominator 0. Okay, so do you understand why those are vertical asymptotes?
Yes, sir.
Okay. Then horizontal asymptotes. Couple characteristics about horizontal asymptotes. Horizontal asymptotes are going to be horizontal lines then. The graph approaches. This is an important note. Horizontal asymptotes can be what?
Cross.
Okay, horizontal asymptotes can be crossed. Guys, take a look at this graph right here. Looks like it runs out. Looks like this is going to flatten out next to the what here, kids?
0.
Okay, so at y equals 0 or the x-axis, same thing over here. Looks like it's going to flatten out where?
0.
0. But if you look at this graph right here, did it flatten out at 0 or did it do something else?
Oh, gosh darn it.
Cross 0, didn't it? So it's possible that you get graphs that have a horizontal asymptote, but part of the graph might cross that horizontal asymptote. Horizontal asymptotes are typically used to monitor or to look at end behavior, which we'll talk about here in a second. Okay? Horizontal asymptotes, in this case for the graph here, the x-axis, those are typically looked at in terms of end behavior. And I'll show you what I mean here in a second. All right? But what kind of asymptotes can be crossed? Horizontal. Okay? Horizontal asymptotes. You can make them match. Just don't cross a vertical asymptote. If you do that,
Then you are going to be in trouble.
okay? All right, next page. You ready for next page, kids? Anybody need more time with that one right there? Okay. Hey, somebody remind me to pause the recording when we come, or when we leave for lunch, and then when we come back from lunch, remind me to. All right, resume. Okay. Kids, we need to talk about some rules of polynomial functions. So I think it's important right here to know the characteristics or the shapes of polynomial functions. So I'm going to just make a little cheater chart here. Is that okay with you guys? Okay. We're going to talk about functions of degree 2, degree 3, degree 4. Did I skip a page? No. Degree 5. Is there enough for degree 6?
There is another second.
Is that good? Okay. So, let's just talk real quickly, kids. A degree 2 function, what kind of graph would that be?
This. Touchdown.
Yep. A U shape, right? Okay. I wish that our school would change our logo to the parabola U. That would be so cool.
Or-
Right by like
Or.
Oregon, right there.
Or we could do
Oregon.
this.
Yeah.
Utah.
Ours?
Ours is off of Utah, yep.
Yeah.
Okay. All right. If anybody in Utah is listening to this, you didn't hear that. All right. Example right here will be like y equals 2x squared. When I put this 2 out in front and I have this positive k up here, we're saying that the leading coefficient is what kind of a value here, kids? Yeah, so these plus k minus k just means leading coefficient. Squeeze it in here. It means leading coefficient. Okay, so the leading coefficient in that is going to be two. And the shape of this graph is a parabola. It's a U shape. So if a U shape is what comes about in a degree 2 polynomial function when the leading coefficient is positive, what kind of graph is going to come about when you have a negative coefficient? Yeah, it's like the arch, right? I have a t-shirt at home, St. Louis arch, y equals negative x squared plus 630.
Is that a parabola?
And did you also know that over there in that arch, that 630 represents the vertex? How high above the ground it is, 630 feet. You know that? Pretty cool, huh? How many of you have been in the arch before? It's goofy. Riding up in that thing is, I tell you what, I don't really get claustrophobic, but when I got in that pod, it was like we were riding up that thing. It's like, I don't know if I like this or not.
It's like going up and then.
Okay.
We tried to, and it was close.
Okay, third degree function. I'm going to sketch these shapes for you. I want you to do the same. Now guys, sometimes a third degree function might also look like this. It might come up, it might flatten out, and it might take off this way. You've seen x to the third like that before. Or they might come out like this, flatten out, take off this way. Okay, sometimes they're bumpy, sometimes they aren't bumpy. Okay, and when I talk about bumpy, I'm talking about peaks and valleys of stuff. Okay, talking about peaks and valleys of stuff. Okay, so I want to talk right here. How many peaks or valleys did this quadratic have? One. At most, how many peaks and valleys does this cubic function have? What do you think the most number of bumps is going to be on a function that is a fourth degree?
0, 1.
3. Okay? Leading coefficient like this typically makes a W. It could be like this, or it might flatten out kind of like this. But regardless, kids, if a graph has, and listen to how I say this, if a graph has, in this case, a fourth degree graph, the most number of bumps or peaks and valleys it can have is 3. Okay? The most number of peaks and valleys it can have is at most one less than a degree. Now I'm not going to draw all of these, but I'm going to draw them with the most. So this is what negative k would look like with 3 bumps. Okay? At most, how many bumps for a fifth degree function? Okay, and this is what your graph would look like. Here's 1, 2, 3. That's what this is going to look like. Anybody seeing a pattern with these at all? Especially when it comes to even functions and odd functions, or I should say even degrees and odd degrees.
It's this. Bam, bam.
Yep.
Bam, bam.
If the degree is even and the ends go like this, the ends of the graph go like this, what's my leading coefficient? Positive or negative? Positive. If I'm dealing with an even degree and my ends go like this, what's my leading coefficient? If I have odds where the ends go like this, what's the coefficient? And what about this? Okay. So I'm going to tell my runners in track, negative, positive, negative, positive. Going like this at the end of the race.
That's pretty positive.
Or just a ball over.
Anybody got to guess what this graph's going to look like?
Almost a
Okay. At most, how many bumps for a sixth degree function, kids? Looks like a camel, doesn't it? Here's your head and the humps and its tail. And if I just put some legs on it, I have a camel.
You ever ridden on a camel?
No. No, camels scare me.
Llamas are even scarier once I found out they can spit.
You didn't know that?
Not when I was little.
At most, how many bumps do I have here? 1, top 2, bottom 3, top 4, bottom 5. And then this one here will look like, huh? Okay.
It's not a function because it doesn't pass the horizontal line test.
Well, it wouldn't be invertible. It is a function because it passes the vertical line test, but it's not invertible. It's not invertible because it would fail the horizontal. Okay. All right, let's take a break there. We're going to start looking at end behaviors when we get